Okay, now we pass to the next section. This is called indefinite integrals now in general. Okay. So indefinite integral, well, we had definite integrals. Indefinite integral is a scientific name, polite name for antiderivatives. Okay, so when you say antiderivatives, almost everybody understands what you are talking about, but that's not nice. So you have to invent a new name so that people will think that you are doing something very complicated. Okay, so this is polite way of saying antiderivatives. Okay. One nice thing about this indefinite integral stuff is that since antiderivatives are used for integrals, and since we have a notation for derivative, we want to invent a notation for antiderivatives. So we use the integral sign without any endpoints. Okay. So if f prime of x equals f of x, we write integral f of x dx, or integral just f. Okay. We write integral f of x, or integral f, or integral of f of x dx for f of x. Okay, so you see we are not evaluating this. We are just saying that we are talking about a function whose derivative gives me the function I write here. And sometimes I want to make sure that I'm mentioning x as a parameter. Okay, so for example, we use this thing, integral x squared, or integral x squared dx is equal to, okay, 1 over 3 x cubed plus c. Now c is important. Okay, so because by taking the antiderivative, you are producing something and you are promising that whoever needs this antiderivative can use your antiderivative. If you put 0 here, then only those people who need the constant 0 can use it. Okay? Because as I mentioned to you, the antiderivative means you are talking about functions. So the graphs of these functions are something like this. Okay, so this is x, y. So the graph of this function is probably something like this. Okay, so this is when the constant is 0. This is when the constant is negative. Okay, so you see that these are all the same curve. Nothing changes. You take the same curve, you can move it up and down. Okay, the tangent line at every point, if you choose an x here, okay, so the tangent line is always the same. Okay, but where the function passes is different. So these things later on, when you take differential equations, this property, how to define this, depends on where your curve passes, and where your curve passes is called the boundary condition. Okay, so you want to find the function whose derivative is x squared, such that the function is 5 at the point 7. Okay, so that happens. Okay, so you need that in your calculation. So then you take the antiderivative, you put your c here, and later on decide for your particular purpose what the c should be. This c does not change the derivative, but it changes where the function passes. Okay, so let's review some properties. Of indefinite integrals. Okay, so we know that we did these things under a different name. Okay, so first of all, if you have a constant times, I have a function, a constant times f of x dx, Okay, so I'm interested in the antiderivative of this. So this is c times f of x dx. So what other easy things? I have integral f plus g. Let me write it. Let me use this notation now. F plus integral g, but not. So in the excitement, in the stress of the exams, you invent such rules, but such a rule does not exist. This is not, well, two nuts. Okay, so maybe I put this not here, but this is not integral of f, integral of g. Okay, so obviously this does not hold. If you think about this for a fraction of a second, you'll immediately realize that if I take the derivative of this, I will not get this. Okay, so that's, but in the exams, you'll invent all sorts of new theorems. Okay, so just keep in mind, try not to invent new theorems in the exam, because if you invent it in the exam, the chances are that it is wrong. But if you invent it in your own time, if you check it over several times, if you are convinced, then it is correct. But in the 5 minutes you need a theorem, you say, I need a theorem, so maybe it is true. It doesn't work, okay? It also happens in high-level research also. You come to a point where you definitely need a condition to pass from here to here. How can you resist it? You put the condition, you pass from there, you obtain all sorts of wonderful results, and then you come back and check the condition, you find that the condition never holds, okay? So the same thing holds in the exam, in research. Be careful about that. Okay, so what other things? You always have these things, dx. This is cx plus a constant. Okay, so this big C is an integration constant. This is a fixed constant. Okay, so this is an integration constant. So I'm doing this deliberately using the same thing, so that you don't follow the notation. You don't follow algebra blind. You just use these things. They have whatever meaning you assign to them. Okay, so we have this. So we have the rule xn is equal to 1 over m plus 1 x m plus 1 plus c when n is different than minus 1. What other things we have? Sine x is minus cosine x plus c. Cosine x dx is sine x plus c. Then we have the usual things. I think secant square x dx. So this is tangent, right? Tangent x plus c. There is also rules for cosecants and cotangents, but I will not go into that because I can never memorize them. So secant x, tangent x, dx is what? Secant x plus c. Of course, then we have secant x dx equals what? Well, we will do this later. After we do logarithms, there's a nice trick to find this, but it is not immediate. But this was used in cartography even before the actual invention of integrals. So that's why it has a historical meaning. Okay, so note the tables will give, for example, integral 1 over x squared dx equals minus 1 over x plus c. Okay, so it doesn't mean that, for example, if you are going to use this, where are we going to use this? Okay, we are going to use this to evaluate definite integrals. You look, you break the function into smaller parts, and eventually you look at a table, or you look at your memory, and then you evaluate this. Okay, so if your indefinite integral, as I mentioned last hour, is from minus 1 to plus 1, this is the antiderivative. You don't evaluate this from from minus 1 to plus 1. Okay, so these tables always means that the use at your own risk. Okay, so that's what the tables always say. If it doesn't make sense, then obviously you will not use it. This property holds when this function is defined and continuous on an interval. If your interval includes 0, then that condition is not satisfied, so don't use this. Okay, so the tables require your intelligence and your conscious manipulation. Okay, so that's this one. Okay, let's do. Sometimes, of course, just because you learned something new doesn't mean that you have to use it everywhere. Okay, there is even a proverb saying that give somebody a hammer and he thinks everything is made of nails. So, for example, but use your own intelligence. So find the area x, y. The function is x equals 2y minus y squared. So it's a parabola like this. Okay. Find the area. Find the shaded area. Okay, just because we learned to take the integral of functions y equals f of x, you can solve for y from here, divide this by 2, find this area, then find this area, subtract this rectangle here, etc. Okay, well, that's one way. And if you do it, everybody will say oh olsun to you. Okay, but because there's an easy way, just try to live on this axis. Then you have a function saying that the value of the function can be given in terms of your parameters like this. So just integrate it from here to here, this function. Okay, so just integrate. So what is this number here? I didn't write it here. So when x is equal to 0, y is 2, right? So this is 0, this is 2. So integrate from 0 to 2. 2y minus y squared dy. Okay, so what you are doing is you are considering Riemann sums like this. Okay, and then taking the limit. The function is continuous, so the limit exists, and the limit is expressed with this symbol. Now you use the usual rules. Okay, you can integrate 2y, you can integrate y squared, evaluate it, and you can get the area. Okay, so that part is easy. So another thing is something like this. So before you plunge into using algebraic manipulations and calculus, you just take your time, stop for 30 seconds, stare at the problem, and see what is actually involved. Maybe there's an easy way to do it, so you don't waste your time. So this is something like this. This is y equals 4th power of x. And this is 1, 1. And we want the shaded area. Okay, so now just because we tried this here, you can also try it over here, because now here x is equal to 4th power of y from 0 to 1. Okay, so that's one way. X is equal to y to the 4. Integrate along this 0 to 1, y to the 4 dy. Okay, so that is one solution. Another solution is you can now integrate this, but you see when you integrate this, you find the area, this non-shaded area, and you have a square here. So 1 minus integral 0 to 1. This is 1, this is 1. X to the 1 over 4 dx. So this will also give you the answer. Okay. So in these cases, just because you see this, okay, so that's one of the temptations. If you can't think of anything in the exam, you have a function, you take its derivative and hope to get a partial. Sometimes you do. If the midterm is about integrals, you integrate it, then you'll get a partial. Okay, so in this case. But if you stop for 30 seconds, you immediately see the story is quite easy. Okay, so there is another way of working with for definite integrals this time. Okay, So these are, we are now putting together some small properties of integrals along with the big property of fundamental theorem of calculus. So starting from next week, we'll apply these to area, volumes, surface area maybe later. And then we'll look at techniques of integrating complicated functions. So these are just small things here and there. So another way of dealing with definite integrals this time. Average value of a continuous function on A, B. Okay. Now, average generally means that you add n things and then divide by n. Integration coming from Riemann sums is also an addition. Okay, so but there you add millions of things and then you divide by millions. So what we are doing is you calculate the integral of the adding Riemann sums in the limit becomes the integral of the function. So that's the area under the curve. And the average is you divide it by the length of the interval. It has both geometric and algebraic meaning. So what we have this by definition, f average. So we just give a name. F average is a number. We define it. Okay, so this notation is traditionally used in mathematics, saying that the picture I write here has no meaning so far, but from now on it will have the meaning on this side. So I'd better write something meaningful here. I write 1 over b minus a integral from a to b f of x dx. Okay, f is continuous, so definite integral of f exists. This is a number. B minus a is a non-zero number. I divide that number by b minus a, I get a number. Okay, so the right-hand side makes sense. And I call this the average value of f. Now, since f is continuous, okay, so since f is continuous, f has a minimum, say m on a, b, and maximum, say big M on AB. Okay, so f of x is less than or equal to m, less than or equal to small m. I integrate these things. The property of integrals tells me that I will have these things. The inequality is preserved in the integrals. Okay, so this side I know. This is a constant that comes out. This is m times b minus a. This is m times b minus a. Okay. I'm dividing everything by b minus a, so I have m less than or equal to f average. Okay, when I divide this by b minus a, I get this, and we agreed that instead of writing all that crowded thing, we write this simple notation. This is less than or equal to m. Now f is continuous again. So if f takes this number and f takes this number, somewhere in between f takes every value, in particular this value. Okay? So somewhere in between f takes this value. F is continuous. So there is C in AB such that f of C is equal f of f average. Okay. So sometimes we write this as follows. This fact as follows. This is more useful. Okay, so what did we find? We found this thing. Okay. Now let's go back to the meaning of this. We are saying that this thing is equal to f of c. So take this to the other side. We are saying that the integral of f on this interval is equal to some value of c times b minus a. Okay, so remember that this is almost like the mean value theorem. Okay, so sometimes this is also called the mean value theorem for integrals. Okay, so the value of this integral is equal to the length of the interval times some height, and that height is given by value of f at some point. This is when f is continuous. The proof of this thing, well, here it follows that we proved it. We already proved it. But there is an easier way to see why this thing holds. Assume for the sake of this thing, f is always positive. Okay, so this is the graph of f. Okay, so we are trying to find this area. This is a, this is b, x, y, and this is y equals f of x. Okay, so what we are trying to do here is, okay, so now take this side, b minus a, okay, take some height here, okay, so this area you see is less than this one, okay, so increase this height. So if you come, for example, here, then you look at all this height that's larger than this shaded area. So somewhere in between there is a critical point, we don't know where it is, that the purple shaded area is equal to the black shaded area, okay? Because we started from 0, which is less than this number we are trying to understand. We increased it, and now this is larger than the number. So somewhere in between these two things will be, for some particular height, these two things will be equal, okay? Well, now what is important is since f is continuous, this line intersects the curve at some point. So I can take this one as my c, okay? So if f is not continuous, I can still play this game, but instead of f of c, I say that this integral is equal to some number times b minus a. Okay, so that's obvious. But that rectangle, the top of that rectangle will be a straight line like this. Does that straight line intersect my curve or not? Okay, if the curve jumps at that point, then your top of your rectangle may pass there without seeing your curve. But if f is continuous, intermediate value theorem says f takes every value in between, so f will take this value. Okay? So this is called the mean value theorem for integrals or average function. Those the concepts are developed from different points of view, but they give you the same thing. So what is it good for? Sometimes you have this number and you want to bound it, upper and lower bounds for it, etc. So you see that that number is something like this. So if you understand what f is doing, you can bound this number, or you can, if you are multiplying this by something, you know what, how f will react to that, etc. Okay, so these things are useful in calculations. So let me do one more example. Well, this is not here. In the quiz, we will have interpret as a Riemann sum and calculate, etc. So let me solve a problem, which is not the problem in the quiz, but the same type of problem. Okay. So here, interpret this limit as a Riemann sum and find the limit by using the resulting integral. Well, in fact, that's the only way you can find such limits unless the expressions are totally trivial. So here the problem is limit n goes to infinity of 1 over square root n times square root n plus 1 plus 1 over square root n square root n plus 2, okay, dot, 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 plus 1 over square root n plus n. Okay, so we want to calculate this. So this must be the general term, so solution. You start with the general term. The general term is 1 over square root n times square root n plus k, or n plus I, whichever notation you prefer. If this is going to be a Riemann sum, it must be something like this. If it is a term of a Riemann sum, okay, so I'm taking an interval, and each interval is, generally I prefer, first I try 0 to 1 maybe, okay, so later on you can change it. So the length of this thing is 1 over n. Okay, so of course nothing in the problem dictates at this point that you are integrating from 0 to 1, but you try, okay, so that's how you solve problems. If this doesn't work, then you go back and maybe this is not from 0 to 1, maybe this is from 3 to 5. Okay, you check those things later. So I'm trying my luck. It must be something like this, and then here I'll have something. Okay, so how can I obtain this? I must have square root n here and n plus k. Okay, so this is my function. I take this, my f evaluated at some point. Okay, so this must be f evaluated at the beginning point plus k over n. Okay, so I take this over n plus k. So this is square root n over n plus k. So this doesn't look like anything I prefer. I divide both of them by n and see what happens. So this is 1 over 1 plus kn. Okay, so it makes sense. Okay, so if, say, f of x is equal to square root 1 over 1 plus x on 0, 1. Okay, now I check. This is my guess. Okay, so this is not the formal solution. We are playing with the problem, trying to make it look like a Riemann sum. If this works, well, this will work. If it didn't work, you would try something. The only tricky thing would be in such problems, the problem is not from 0 to 1, it's from some other point, then you work accordingly. Okay, so this is f of 0 plus k over n. Okay, so if you do this, this works. Okay, so this is 1 over 1 plus k over n. Okay, so it works. So the limit of this thing, okay, so let me do it here. Okay, so the limit is integral from 0 to 1, f of x, which is square root, well, it is like this now, 1 over 1 plus x dx. Okay, so let's see. Okay, now fundamental theorem of calculus tells me that I have to invent a function whose derivative is equal to this function. Okay? So this is here you are on your own. This is integration. There are no rules. Okay, think of a function whose derivative is 1 over square root something. Well, in the arc students, you don't have square roots there. You have square here. You have 1 minus x squared. That's too complicated. This is a quiz question. In the quiz question, you don't get arc size. Yes? 2 times square root 1 plus x. Okay. So you just check. If we take the derivative of this, this is actually 1 plus x to the power 1 over 2. 1 over 2 comes down, cancels with this. We have 1. Okay, we have 1. And then you subtract 1 from 1 over 2. You get this. Then you multiply it with the derivative of inside, which is 1. So this precisely, the derivative of this is this. Okay? So this is how you check. You make a guess here for these simple things. Then you take the derivative of this and make sure that you get this one. Okay, now the notation is you evaluate this from 0 to 1. Okay, when x equals 1, this is 2 square root 2. When x is 1, this is 2. So this is the answer for this particular problem, and I didn't approximate this thing. So this is the answer. Okay, so this is, in the quiz you'll have a similar problem. Interpret as a Riemann sum, something like this. You take the general term, play with the general term. There are no rules here about how you should do it. Maybe you can find a different, instead of writing this as 1 plus 1, maybe I can, you see here, instead of considering the integral from 0 to 1, I could consider the integral from 1 to 2. Then this whole thing would be x sub k, okay? Because if you start from 1, then you keep adding k over 1 over n to it. At the kth step, you are at the point 1 plus 1 over k. In that case, you are integrating 1 over square root of x from 1 to 2. You'll get something else, but you'll get the same number here. Okay? So the solution to such things is not unique in general. You have to play. Okay, so enjoy yourself. I'll give you the quiz papers now.